My name is Magdalena Musielak. I'm a senior lecturer here at the Mathematics Teaching and Distance Learning Center. And today what I want to show you is the logarithmic differentiation, which is a method of differentiating complicated functions that consist of products, quotients, and power functions all together combined. So let's look at this example here. You have here a product of two functions. One of them is a power function, one of them is a square root, and then you have a quotient on top of all of that. So you could potentially, to find the derivative of this function, you could potentially use your product and quotient rules, but it will be much easier if we use the logarithms and the properties of those logarithms to differentiate this function. So the first thing we do, we apply the natural log to both sides. What we get is natural log of the left equal, of course, natural log of the right. And there you go. Now, if you recall the properties of logs, natural log of a product translates into sum of natural logs. Natural log of a quotient translates into a difference of natural logs. So let's apply these properties to simplify the right-hand side. I will leave the left as is. And now here on the right, I have a product of two functions and then a quotient, which means I will get natural log of the first expression plus, because I have a product, natural log of the second expression minus, because I have a quotient, natural log of the third expression in the denominator. Now, another useful property, if you recall, is that when you have a natural log of expression to a power, this power can be brought down in front of natural log. So let's apply that. 3 is brought down to in front, plus, here you have a square root, which is actually expression raised to power 1/2, so that 1/2 can go in front as well, and minus this last log. And now we have simplified this function as much as we could using properties of natural logarithms, so we are ready to apply the derivative. We take the derivative of both sides, and in each term here we have a natural log, so the chain rule tells us that derivative of a natural log function is going to be derivative of the inside divided by this expression in natural log. So we have f prime of x divided by f of x equals the same rule to each of those expressions. 3 times derivative of the inner part, which is 2x, divided by the inner part, plus 1/2 stays. Derivative of 2x plus 1 is 2, divided by 2x plus 1, minus derivative of x cubed is 3x squared, divided by x cubed plus 4. So there is 1.5 step left. We have to now multiply everything by f of x to move it to the right and substitute our original expression for f of x. So we'll get f prime equals. Now I'll start with f of x, which is this whole big quotient. Times this whole expression. Now we can simplify it a little bit more. We have 6x divided by x squared minus 1. Here the 2's will cancel. We have plus 1 divided by 2x plus 1. And finally 3x squared divided by x cubed plus 4. And that is all. Now you could have, of course, applied your regular product, quotient, and power rules, but finding that derivative would be tedious, and on top of that, once you have found it, you will have to simplify it and put in a lot more additional work into simplification of your derivative than in finding derivative itself. So this is a much faster method. Now, if you were paying attention, and if you remember anything about logs, right at this point, when I took natural log of both sides, possibly you were screaming at me at the screen, watching this. What am I doing? If you remember anything about logs, you know that natural log requires that the function f in this expression be positive. Of course, what if it's not positive? What if it's negative? Well, technically, if f of x is a negative function, what we could do is we could just apply absolute value, take absolute value of a natural log, all of these properties as before apply, and once you are at this step, when you take a derivative of a natural log of the absolute value disappears. So really, we don't have to consider the case of a function being negative, because once we get to this point, this absolute value disappears anyway. And so this, I dare you to try to find the derivative of this function using regular product quotient power rules. This method is much faster.